Hi all, we are picking up today from the guided practice 22 from L'Hopital's rule. And let's just run through some of these examples. So some of these we did in class, but some of them we didn't. So I just wanted to run through them one at a time. So we have one that looks like 1 minus cosine 3x over x. We know this should be 0 because this is a special limit from back in chapter 2. But we can use L'Hopital's rule here to show that that's true. So if we plug in our 0, here you get 1 minus 1 over 0, so that's 0 over 0. And that means that L'Hopital's rule is a candidate here. So this is equal by L'Hopital's rule to the limit as x goes to 0. Again, don't lose your limits. The derivative of 1 is 0, so that goes away. The derivative of negative cosine 3x becomes negative sine 3x times 3 because you have something inside your cosine x. And the derivative of x is just 1. So if we clean this up, this becomes 3 times the sine of 3x. Those negatives will cancel. And now you're going to plug in a 0 here, and that's going to become 0 times 3 is just 0. Okay, so L'Hopital's rule is a way that you can show that that special limit is true. Then let's take it to number 2. If you were to plug a 3 in here, this gives you 9 minus 9 over 9 plus 3 minus 12, and that's 0 over 0. And back in chapter 2, we would have said, okay, this is a indeterminate form. We do more work. And so we would factor this and cancel and see what we get. The other strategy is to use L'Hopital's rule. Because it's 0 over 0, we can use L'Hopital's rule. So equals by L'Hopital's. The limit as x goes to 3. And we take the derivative of the top and the derivative of the bottom. So this is 2x minus 3 and 2x plus 1. Now when I plug in my 3, I get 6 minus 3 over 6 plus 1. And that's 3 over 7. Okay, so factoring is nice, but sometimes L'Hopital's rule can be much, much quicker. Okay. Number 3. This is from another section from back in chapter 2. This one, when we look at our limits at infinity, we would plug this in and say, oh, well, this one's infinity over infinity. And then the long way to do this one is to multiply by everything by 1 over x squared. Hey, review for the final exam, right? Because you got to clear this guy, okay? But we're not going to do that. We're going to say instead of doing that, let's use L'Hopital's rule here. So equals by L'Hopital's, the limit as x goes to infinity, and we're taking derivative of the top over the derivative of the bottom. So that's 8x plus 2 and 6x plus 7. Now, when you take the limit here, plug in your infinities, you still get infinity over infinity. By the way, because the powers are balanced here, I should get 4 over 3 as my answer. Let's see if it works. Okay, we applied L'Hopital's rule. We still got infinity over infinity, which means we can apply a L'Hopital's rule again. As long as it is of the form 0 over 0 or infinity over infinity, you can use L'Hopital's rule. Derivative of 8x plus 2 is 8. Derivative of 6x plus 7 is 6. I don't have any x's, so I can plug in the infinity and I get 8 over 6, which reduces to 4 over 3. And that's exactly what we were expecting. Now, here's where we picked up in class with number 4, and I'm going to go through this step by step one more time. Okay. Now, this one's a bit more involved, okay? So we are going to go ahead and use our L'Hopital's rule here. Now, there's a couple of things that we could do here. And I paused because I saw, hey, guess what? There's a sine x sitting right here. If I multiply the top and bottom by 1 over sine x, I bet I could make some of that cancel, okay? But that still may not help me. So we're going to just jump in here and use L'Hopital's rule if we can. So let's see. If we were to plug in 0, what happens? Well, the top is 0 because x is 0 and sine of x is 0. And on the bottom, you get 0 minus 0. So we definitely get 0 over 0. Okay, so we're going to go ahead and use L'Hopital's rule. And there's some product rules going on here. So if you need to write those out, please do. I'm not going to just for the sake of the length of the video. Okay. But notice that you've got function 1 and function 2. So the derivative of function 1 is the 2x times function 2 is sine x. Plus derivative of function 2 is cosine x. So we leave the x squared and multiply it by cosine x. On the bottom, derivative of sine is cosine x minus derivative of x is 1. Okay, so I have reduced something. That second x became a 1 because my objective is to get to the point where I have something that's not 0 in one of the fractions. Now the top of the fraction is getting worse, but that's okay because the bottom is getting better. If we go ahead and plug in our 0, we're going to get zeros up top because everything has an x in it. And on the bottom, you get 1 minus 1, which is 0. So we're still in L'Hopital's world. So let's take L'Hopital's rule again. This time the bottom is not super complicated. Derivative of cosine is negative sine x. The bad part about that is that when you plug in 0, you're still going to get 0. So we're probably going to have to go one more time. My derivative of minus 1 is 0. Okay, but the top is 2 product rules. So I've got these two, function 1 and function 2. And I've got these two, function 1, function 2. So for the first product rule, derivative of 2x is 2 times the sine x plus 2x times the derivative of sine x is cosine x. For the second product rule, the derivative of the x squared is 2x times the original. And this is going to bother me, so I'm going to go ahead and I'm a little bit of a perfectionist. All right, so that is 1 prime 2 for the second piece for the blue and yellow. Then we're going to keep the x squared, differentiate the cosine. That's negative sine x. Okay, so now I've got something with 4 terms. Now, we already said that if we plug in a 0 in the bottom, I'm still going to get 0. And up top, everything has a 0 except the first term. And when you plug into sine, that's also 0. Because sine of 0 is 0 and x is 0. So anything with an x or a sine is going to be 0. And that's going to give me a 0 on top. So hopefully this will be our last go round. But we do have to do this. And there are 3 product rules. So 2x times cosine, 2x times cosine, negative x squared times sine x. So here we go. One more time with L'Hopital's rule. You can do L'Hopital's rule over and over and over again. The key is making sure that it's getting closer to being solved as you go. All right, 2 stays. Derivative of sine is cosine. Plus the derivative of 2x is 2 times the cosine. Plus derivative of cosine is negative sine, so we're actually going to subtract. So the 2x stays, derivative of cosine is negative sine. On to the blue and orangey color. So the derivative of 2x is 2 times the cosine x. Oh, I could have combined those 2 middle terms and made it 4x cosine x. Ooh, that would have made my life easier. Okay, but I didn't see it, so that's fine. So 2x derivative of cosine is negative sine. Now for the last one, minus the derivative of x squared is 2x times the sine x minus x squared, and the derivative of sine is cosine x. So that is one big term. But the good news is most of those are going to be 0, right? And on the bottom, the derivative of negative sine would be negative cosine x. And now we're plugging in 0. So here are the things that are going to be 0. Any term that's got an x in it. So this one's 0, this one's 0, this one's 0. Oh, I missed an x. Also, this one is 0. And that means I have 2 cosine x, 2 cosine x, and 2 cosine x. So that's going to give me 2, because cosine of 0 is 1, plus 2, plus 2. And in the bottom, cosine of 0 is 1, and that's negative 1. So I'm going to get negative 6. Okay, so that's quite the process. 3 different times, lots of product rules, but totally doable. Okay. All right, now I started this one in class, and I actually led you down the wrong path, but that's okay, we're going to fix it. Because when we see things, so our fractions are automatically 0 over 0, and infinity over infinity are indeterminate forms. Other things that form indeterminate forms, 0 times infinity, infinity minus infinity, and infinity to the 0, and 1 to the infinity. Okay, these are all indeterminate forms. So how do we handle these? Well, we really just use algebra to turn it into fractions so that we can use L'Hopital's rule. So the question is, what does that look like? And I'm going to show you 2 examples here. So typically, when it's 0 times infinity, you're going to move something to the denominator, usually using a negative exponent, okay? This one happens to be the infinity minus infinity type, because when you plug in infinity to x and to ln x, you get two infinities, and you're subtracting. How you handle this is you're going to force factor something out. So this is the limit as x goes to infinity, and there's an x here. There's not an x here, but I'm going to force it to be factored out. So I'm going to move this x out front. When I take it out of the x, that's 1. And then to take it out of the ln x, I'm going to have to divide that term by whatever I pull out, right? If you think about it, if you had 4x plus 10, then they both have a 2 in common. And in order to get what goes inside, you take the original divided by the 2. So that's 2x plus 5. So we're going to do the same thing here. It's just not going to be as pretty. So we're going to take the original, which was the ln of x, and we're going to divide it by what we factored out, which is the x. Now, what that means is now I have a fraction to work with, okay? Because I can figure out what the limit of that piece is and then plug that in, okay? So I'm going to kind of do a side note here. So we're going to look at the limit as x goes to infinity of ln of x over x. Well, if I plug in infinity here, that's infinity over infinity. So that means I can use L'Hopital's rule. And derivative natural log of 1 over x, and the derivative of x is 1. Plug in your infinity, that's, this is just going to be 1 over x, so when you plug in the infinity, that's 1 over infinity, which we know is 0. So that means when I plug into here, this is x goes to infinity times 1 minus, and the ln x over x becomes 0. And that will be infinity times 1, which is just infinity. Okay. So you kind of force factor to create that fraction. Then, because it's kind of inside other things going on, you're going to go ahead and kind of pull that out and say, oh, let me use L'Hopital's rule on just this part. Then see if I can plug it back in and make it work. Okay. And then lastly, whenever you have powers, here's how we handle powers. You're going to, this becomes, when you plug in infinity, this is infinity to the 0. Which means we want to use L'Hopital's to solve this, but we don't have a fraction involved. So here's what we do instead. We're going to use e's and ln's to get the exponent out of to get the variable out of the exponent. So we're going to do the following. We're going to make this equal to the limit as x goes to infinity, e to the ln of whatever I've got. Okay. So I use both an e and an ln. Why do I use both? Well, they cancel each other out, right? So I have not changed the function. That's super important. I haven't changed the function because this just reduces back to x to the 1 over x. But because I have the ln up here, I can use the properties of ln to bring that down in front. So that's what I'm going to do next. So I'm going to make this the limit as x goes to infinity, e to the, if I bring the 1 over x, it comes down in front of the ln. It looks like this. Then I'm going to make that look like one whole fraction. So that's e to the ln of x over x. And now this is my fraction that I can use L'Hopital's rule with. So I'm going to go over here to the side, the limit, and we just did this, but we'll do it again, of ln of x over x. That's infinity over infinity. So we can use L'Hopital's rule. That's 1 over x all over 1. And we plug in our infinity, that's 1 over infinity, which is 0. So I can put that back in here as I'm evaluating my limit, and that's going to give me e to the 0, and e to the 0 is 1. Okay, so we use that ln of an e to get that exponent out of there. That way we're not working with powers to powers. Okay, and that's going to be it for our guided practice.